Home. For 8 billion people, this blue marble spinning through the void is the only home we've ever known. But Earth wasn't always this paradise. 4.5 billion years ago, where you're sitting right now was part of a hell beyond imagination. This is the story of Day 1, the most violent, most spectacular day in our planet's history, a day that lasted 10 million years. This is the Genesis, the birth of Earth. Before Earth existed, before the sun existed, there was only darkness and cold. But hidden in that darkness was a secret, a cosmic recipe that would create everything you see around you. The story of Earth actually begins with death, the death of a star. 4.6 billion years ago, somewhere in our galaxy, a massive star reached the end of its life. In its final moments, it exploded with the force of 100 billion nuclear bombs, hurling its guts across light years of space. That shockwave hit a cloud of hydrogen gas and dust, what we call a molecular cloud. And when it did, it triggered something remarkable. The cloud began to collapse. As the cloud collapsed under its own gravity, it began to spin, faster and faster, like a figure skater pulling in their arms. Within a few million years, that spinning cloud transformed into something new, a flat, rotating disk of gas and dust, the Solar Nebula. At the center of this disk, material was piling up, getting hotter and denser. Eventually, the pressure and temperature became so extreme that hydrogen atoms began fusing together. The sun was born. But our star didn't create a solar system, not yet. Surrounding the newborn sun was a disk of leftover material, dust, gas, ice, and metal, spinning in orbit. And hidden in that chaos were the seeds of Earth. But how do you build a planet from dust? The answer would surprise even the most brilliant scientists. Imagine trying to build a house by throwing sand in the air and hoping it sticks together. That's essentially what the early solar system had to do, but nature had a trick up its sleeve. When we examine ancient meteorites, rocks that have survived unchanged since the solar system formed, we find these tiny spheres called chondrules. They're droplets of rock that melted and then rapidly cooled in the solar nebula. These microscopic beads of rock became the building blocks of planets. But there was a problem. Particles in orbit around the sun are all moving at slightly different speeds. When they collide, they usually just bounce off each other or shatter. For planets to form, somehow these grains needed to stick. For decades, this was one of the biggest mysteries in planetary science. How do you get past what scientists call the meter barrier? The answer involves static electricity, turbulence in the gas disk, and something called streaming instabilities. Basically, that doesn't stick together one grain at a time. Instead, dense clumps form in the disk, and gravity takes over. Once objects reached about a kilometer across, their own gravity became strong enough to pull in more material. These boulder-sized to mountain-sized objects are called planetesimals. And within just 100,000 years, the solar nebula was full of them. Now the real violence could begin. The early solar system was like a cosmic shooting gallery. Millions of objects, all in intersecting orbits, all smashing into each other at thousands of miles per hour. Most collisions were destructive, planetesimals shattered into fragments. But occasionally, two objects would hit at just the right angle and just the right speed. Instead of destroying each other, they would merge. The big got bigger, and the biggest became protoplanets. In the region that would become Earth's orbit, one protoplanet was winning the cosmic lottery, but its victory would come to a terrible price. 4.5 billion years ago, about 50 million years after the Sun formed, a protoplanet circled in what would become Earth's orbit. It was smaller than our planet today, roughly the size of Mars, but it was growing fast. We call this stage runaway accretion. The Proto Earth had become massive enough that its gravity dominated its orbital neighborhood. It was essentially vacuuming up everything nearby. Every day, thousands of impacts. Every impact released energy. When something moving at cosmic velocities, 10, 20, 30 kilometers per second, hits a planet, that kinetic energy converts instantly to heat. A lot of heat. The Anthropocene Earth had no chance to cool. Each new impact melted more rock, added more heat. The entire surface became an ocean of magma, hundreds of miles deep. Imagine an ocean of liquid rock, temperatures exceeding 1200 degrees Celsius, over 2000 Fahrenheit, hot enough to melt iron. And it's not calm. There are waves hundreds of feet high, made of molten silicate. Above this hellscape, the sky itself was an extension of the inferno. The atmosphere, if you can call it that, was made of vaporized rock, silicate clouds. The sky would have glowed red from the heat radiation below. This was Earth in its infancy, a world hostile to everything we think of as earthly. No water, no air, no solid ground to stand on, just heat, violence, and chaos. But deep beneath that magma ocean, something crucial was happening, something that would determine the fate of our planet. Proto Earth first formed was a jumbled mixture, iron, nickel, silicate rock, all mixed together. But iron is much denser than rock, and gravity doesn't like disorder. What happened next is something we call the Iron Catastrophe, though honestly it was less of a catastrophe and more a crucial organizing event. In the magma ocean, droplets of liquid iron began to form, and they began to sink. Iron is almost twice as dense as the silicate rock that makes up most of Earth's mass. So these iron droplets, once they got large enough, fell through the magma toward the center. And when I say fell, I mean fell fast, potentially reaching the center in just a few thousand years. Trillions upon trillions of tons of iron raining toward the center of the planet. This released an enormous amount of gravitational potential energy. Think of it like dropping a bowling ball off a skyscraper. When it hits the ground, that energy has to go somewhere. Now imagine dropping enough bowling balls to fill the Grand Canyon from hundreds of miles up. The Iron Catastrophe added so much heat that it remelted rock that had started to solidify. It kept the magma ocean liquid for millions of years longer than it would have otherwise lasted. But it also accomplished something essential. It gave Earth a structure. The iron sank to the center and formed Earth's core. The lighter silicate rocks floated above, forming the mantle. This differentiation into layers, core, mantle, and eventually crust, is what makes Earth a geologically active planet. And that core, that iron heart of our planet, would eventually create something else, something that would make Earth uniquely suited for life. Earth's magnetic field, generated by liquid iron moving in the outer core. That magnetic field protects us from solar radiation. Without it, life as we know it would be impossible. So in a sense, the Iron Catastrophe wasn't a catastrophe at all. It was the beginning of Earth becoming Earth.
But Proto Earth's trials were far from over. The worst was yet to come. About 50 million years after the solar system formed, Proto Earth had swept up most of the material in its orbit. The bombardment was slowing, the magma ocean was finally beginning to cool, a thin crust was forming in places. For the first time in its short existence, Earth was approaching something like stability. But in the cosmos, stability is fragile. There was another planet, we call it Theia, after the Greek Titan who was the mother of the Moon. It had formed elsewhere in the solar system, but gravitational interactions with other planets had destabilized its orbit. Theia was on a collision course with Earth. Computer simulations show that Theia was probably about the size of Mars, roughly 10% of Earth's mass, and it was moving at about 4 kilometers per second when it hit. That's nearly 9,000 miles per hour. Nothing, not the asteroid that killed the dinosaurs, not the largest volcanic eruption in Earth's history, nothing compares to what happened next. The impact wasn't head-on. Theia struck Earth at an oblique angle, about 45 degrees. This was actually crucial for what happened next. When Theia struck Earth, the force of the impact was equivalent to several billion nuclear bombs detonating simultaneously. Both planets were instantly vaporized at the impact site. A shockwave tore through both bodies at hypersonic speeds. The energy was so intense that rock didn't just melt, it vaporized, it turned into plasma. Earth didn't just shake, it rang like a bell. Seismic
waves propagated around the entire planet, each one powerful enough to remelt any crust that had formed. The impact probably lasted only a few hours from initial contact to the settling of the debris, but in those few hours, both planets effectively ceased to exist in their original forms. Most of Theia's iron core sank into Earth's core, increasing our planet's mass and spin. But a vast amount of material from both Earth's mantle and Theia's was blasted into orbit. Our simulations show that within a day, just 24 hours, this debris began to coalesce. Within a year, it had formed a single large body, the Moon. The Moon formed so close to Earth, maybe only 15,000 miles away, compared to 240,000 miles today, that it filled a huge portion of the sky, and both bodies were still molten, glowing like embers. Earth had been reborn, larger, spinning faster, and no longer alone. But it had also been reset to zero. The entire surface was molten again. The magma ocean was back. Day one would have to start all over again. But this time, something different would happen. This time, Earth would begin its transformation from hell to home. After the moon-forming impact, Earth was a glowing ball of molten rock. The surface temperature exceeded 2,000 degrees Celsius. The sky was filled with vaporized rock. Nothing remotely like life could exist anywhere on or near this planet. But slowly, very slowly, things began to change. Heat has to go somewhere. Earth was radiating energy into space through thermal radiation, basically glowing in the infrared, and as it did, it cooled. The first crust formed, not a permanent crust. Frequent impacts still broke it up and remelted it, but solid rock was appearing on the surface. We think the first solid crust was made of dunite and komatiite, ultramafic rocks that can form at extremely high temperatures. These rocks are rare on Earth today, but they would have been common on the early planet. This early crust was temporary, constantly destroyed and reformed, but each time it formed, it lasted a little longer. The magma ocean was freezing from the top down. Within about 10 million years after the moon-forming impact, Earth had a relatively stable crust, thin, frequently recycled, but solid. 10 million years, it seems like an eternity to us, but in geological time, it's the blink of an eye. But Earth was still a dead world. The surface temperature was still hot enough to glow. There was no ocean, no air we could breathe, and the asteroid bombardment continued. This period, from about 4.5 to 4.4 billion years ago, we call the Hadean Eon, named after Hades, the Greek underworld. It's an appropriate name. But hidden in that hellscape were the ingredients for transformation, because as Earth cooled, something extraordinary was happening in its atmosphere. Something was falling from the sky, something that would change everything. Earth's early atmosphere was nothing like today's. There was no oxygen. That wouldn't come for billions of years. Instead, the air was thick with carbon dioxide, nitrogen, water vapor, and volcanic gases. Where did this atmosphere come from? Some of it was captured from the Solar Nebula during Earth's formation, but most of it came from volcanism and outgassing from the interior. And among those gases was something crucial: water. For a long time, scientists debated where Earth's water came from. Did comets deliver it? Asteroids? The answer is yes, but also Earth had water built into it from the beginning. The planetesimals that built Earth contained hydrated minerals, rocks with water chemically bound into their structure. As Earth heated up, this water was released into the atmosphere as steam. After the moon-forming impact, Earth's atmosphere was essentially a steam atmosphere, immensely thick, hundreds of miles deep, at impressive pressures, and it was hot, potentially thousands of degrees at the surface.
But as the surface cooled, something remarkable happened. When the surface temperature dropped below about 100 degrees Celsius, the boiling point of water, the steam could finally condense. And when it did, it fell as rain. The first rain on Earth. At first, raindrops hit the hot crust and instantly flashed back to steam. The rain lasted only seconds before boiling away. But as the crust cooled, the rain lasted minutes, then hours. Eventually, you get to a tipping point. The surface is cool enough that water can stay liquid. And when that happens, you get what might be the longest rainstorm in planetary history. It rained, and it rained, and it rained. For thousands of years, perhaps hundreds of thousands of years, water fell from the sky and began to fill the lowest places on Earth's surface. The entire inventory of Earth's water, all the oceans, all the ice, all the water in the atmosphere, fell as rain during this period. It was the birth of the hydrosphere. By about 4.4 billion years ago, just 150 million years after Earth formed, our planet had oceans. These weren't oceans like today's. They were hot, maybe 80, 90 degrees Celsius. The water was acidic, loaded with dissolved minerals and gases. The sky was orange-gray from volcanic aerosols, but they were oceans. Earth had crossed a threshold. It was no longer just a ball of molten rock. It had become a water world. But these new oceans faced an enemy from the sky, an enemy that would threaten to destroy everything Earth had built. For about 100 million years after the oceans formed, Earth continued to cool and stabilize. The bombardment from space was slowing. Continental crust was beginning to form. Earth was becoming a more hospitable place. But 4.1 billion years ago, something changed. In the outer solar system, the giant planets Jupiter, Saturn, Uranus, Neptune were still migrating, still settling into their final orbits, and as they moved, they stirred up the asteroid belt and the Kuiper belt. Millions of asteroids and comets were thrown out of their safe orbits. Many were ejected from the solar system entirely, but many others fell inward toward the Sun, toward Earth. The late heavy bombardment had begun. Evidence from lunar samples shows that about 4 billion years ago, the rate of impacts increased dramatically. The moon's surface was saturated with craters, and if the moon was being hit that hard, Earth, with its much larger cross-section and stronger gravity, was being hit much, much harder. Some impacts were large enough to vaporize the entire ocean. An impact by an asteroid just 200 kilometers across, and we know larger ones hit Earth, would have enough energy to boil away the entire ocean, turning it back into a steam atmosphere. Earth was being reset again and again. Each large impact undid millions of years of cooling and stabilization. This went on for several 100 million years. It's possible that the oceans evaporated and reformed multiple times during this period. And yet, Earth endured. After each impact, the steam condensed again. The rains returned. The oceans reformed. Life, at least certain kinds of life, may have even persisted through this period, perhaps in protected environments deep underground or in hydrothermal vents. Earth is resilient. It's been through hell, literally, multiple times, and each time it's rebuilt itself. By about 4.8 billion years ago, the late heavy bombardment was over. The solar system had finally stabilized, and Earth could begin its transformation into the planet we know today.